Okay, good afternoon slash good evening. So I'm going to cover the rest of lecture set 3 in this session. The last topic that we have to cover in this lecture set is the review of paired t-tests, which are the two sample procedure that we would utilize when data is not, or when our two samples of data are not independent of one another. Before I start working through that, just as a reminder, this week we've predominantly been working through lecture set 3. We started the week by finishing off or working through a few examples of single sample t-tests. Last lecture, we got into the bulk of lecture set 2 and we worked through an illustration of the independent two sample t-test. And today we're working through the last procedure, which is the paired two sample t-test. As a reminder, the lab assignment is due on Monday, January 25th, and next Friday, the 29th, we will have our first quiz, which will be held during class hour, so from 1 p.m. to 2 p.m. And that quiz will be done from home, and all answers will be submitted on CrowdMark. So you will be sent the question sheet, roughly 5 to 7 minutes or so before 2 o'clock, and then you'll have from 2 until 3 to get all of your answers in to CrowdMark. Any submission after 3 o'clock will be considered late and will be awarded no marks. So it's imperative that you have everything done, photos taken, and uploaded to CrowdMark by 3 p.m. And I'll give more details about the exam as we get closer to it. With that being said, the first quiz will cover all of the topics that we have studied so far, including the paired t-test. So the first quiz is going to cover lecture sets 1, 2, and 3. Okay, so let's get into the material for today. So as I mentioned, what we're talking about here are the paired, the paired t-test, which is what we use when we have what we refer to as paired or dependent samples. So we distinguish between the two sample hypothesis testing and two sample confidence interval procedures that we are working on based off of the structure of the data. The examples that we have seen so far, so for example, we looked at the dynamic system versus the static system for recovery from surgery in the hospitals. We considered each of those samples to be independent. When we have multiple measurements on the same observation, we will typically observe what we call paired data. Now, in this particular example, what I mean is when we have two measurements on the same observation. You can have more than two measurements on the same observation, but we're only focused on two variables per observation in this case. So when we record two values on the same observation, we build what is called paired data. So each observation has two different measurements. For example, your weight in the morning and your weight in the afternoon. We cannot assume independence between each of the samples because the observation is the same within each sample. So in this case, we need to use a different style of test in order to compare the population means from each of the populations that we are studying. So weight of all Albertans in the morning versus weight of all Albertans in the afternoon, for example. Okay, so one of the ways that we can tell that we're working with paired data is, again, because each observation is going to have two variables associated with it. When we are working with paired data, just make sure I didn't skip over anything here. Right. So when we are working with paired data, we formulate what are called the differences between each of the values per observation. So essentially what we are doing is we are creating a one sample t-test where we apply that one sample t-test to what are called the differences. And the differences are literally just, for each observation, the difference between the two variable measurements for each of those observations. Our null and alternative hypothesis are effectively the exact same as they were in the independent two sample case, though we usually use the term or the symbol mu subscript d in our null and alternative hypothesis. So this would represent the population mean of the differences. Right? Now, once we have our samples collected and we compute our differences. To estimate the population mean difference, we simply take the mean of the differences and the standard deviation of the differences. And then we can build a test statistic based off of those quantities. So again, the paired t-test and the paired confidence interval are really just one sample t-tests, are really just the one sample t-test and the one sample confidence interval, but applied to a variable that we have to calculate ourselves. So if we want to construct a confidence interval for the differences in a paired situation, then we begin by checking the assumptions. These assumptions are the same as they were in the one sample case, except they're being applied to the differences themselves. So the first assumption is saying that all of the differences were randomly selected. This is the same thing as saying all of the observations in the data set are randomly selected. So even though we cannot assume independence between the samples or between the variable measurements for each observation, we can assume that each observation themselves were randomly selected, or we do assume this when we start the test. The central limit theorem would apply in the same way that it applied in the one sample case or it applied in the two sample case, except again, what we are doing is applying them to the differences this time. So we either have some information that the two populations that we are working with are both normal, such that their differences would also be normal, or we collected more than 30 observations such that the central limit theorem would apply to the differences. So it's a standard type of hypothesis checking procedures that we would go through in the one sample or two sample cases, except we would typically only refer to the differences, so we wouldn't have assumptions for each sample separately. Once we have our assumptions checked, we use the usual three-step process to compute and interpret our confidence interval. And as you can see on step 2, the confidence interval formula looks just like a one sample formula, except we have these subscript D's located beside X bar, S, and N. This simply represents that we are taking the mean of the differences, the standard deviation of the differences, and we are counting the number of differences, but ND would be the same as the sample size, even if you didn't count the number of differences. All right. Our hypothesis test will have the usual 6 steps. As I mentioned before, we typically structure the null and alternative hypothesis around mu d, which is the population mean of the differences. You'll notice on step 1 here, I have the 3 possible null and alternative hypotheses we might see in a paired t-test. You will notice that these are the two-tailed test, the upper tail test, and the lower tail test respectively, based off of the symbol in the alternative hypothesis. And again, what you should be able to see is this looks very much or is very similar to the one sample t-test that we studied before. In fact, even the degrees of freedom is simply the number of differences minus 1 in this case. So the trickiest part of conducting a paired t-test is actually establishing that you are working with dependent samples and then going through the process of computing the differences, recognizing that the direction of the difference does play a major role, as the direction of the difference will influence whether you are conducting an upper tail test or a lower tail test. And this is a similar idea to what we talked about last class when we talked about how we should designate one population as population 1 and the other is population 2, so that we know if we are comparing, so that when we do perform a directional test, we can say, okay, this is going to be mu1 bigger than mu2, which is right-tailed, or mu1 less than mu2, which is left-tailed. All right, once we have our alternative, our null and alternative hypotheses constructed, it's the standard procedure for completing the test. And sorry, I should also mention that we're strictly focusing on the student t distribution in this case, because we would never have the population standard deviation of the differences. This would always have to be estimated. Okay, so let's look at an example of a paired t-test. So in this example, we have 8 different cows. Okay, so the cow number here, this is the observation. Okay, so that means that we have little n is equal to 8, which means that we will also have little nd being equal to 8. So the sample size experiment, and the sample size for the number of differences will always be the same. So we have 8 different observations, 8 different cows in this experiment. Each cow is fed one type of diet for a month, and over that month, their milk production is calculated. So in 1 month, they are fed the current diet, and then in the next month, they are fed this new diet. Now, each month on each diet, the milk production for the cow is measured. So we are creating a naturally paired structure here because we have 2 measurements per cow. Okay, or per observation. And that is really the key to recognizing a paired structure in the test. So if for each observation you have 2 different measurements, that is the paired structure that we were referring to earlier. So we do not have independence between the variable in current and the variable in new, because those milk production values are being measured on the same cow. So anything that would influence milk production that isn't related to the diet would be consistent across both months of the program. Okay. So we want to first determine the direction of the difference. This is important because the direction of the difference determines if we are going to be if we are interested in a directional test, the direction of the difference is going to inform whether or not we are performing an upper tail or lower tail test. Now, it's very easy to find the direction of the difference. It simply refers to how were the differences calculated. So you can see in the last row of this table, we have the differences. So we have 7, 9, -2, 1, 8, -4, 4, and 7. Okay, so each of these values here are being found by taking the new and subtracting the current. Okay, and that's true in every single case. So these are all found by taking new minus current. Okay. So the direction of the difference for part A, we can say the direction is equal to new minus current. All right. Now in part B, we are told given x bar little d, or x bar subscript d is equal to 3.75 and little s subscript d is equal to 4.89, is there evidence that the average milk production increased on the new diet at the 5% significance level? Okay, so breaking this down, we have evidence milk production increased on new diet. Okay, now, since our direction of difference is new minus current, if the milk production has increased on the new diet, we would expect that the values for new will be larger than the values for current. Therefore, we would expect that mu subscript d is bigger than 0. So in this particular case, because we had done new minus current, we would conduct an upper tail t-test because we are asking if there is evidence that the values for new are larger than the values for current. Now, we are also given 2 summary statistics. X bar d is equal to 3.75 and little sd is equal to 4.8. These are respectively the sample mean of the differences and the standard deviation of the differences. So for example, x bar d is going to be the sum from I equals 1 to little nd of the di divided by little nd. Okay, so this is going to be, for example, 7 plus 9 plus -2 plus -4. Well, might as well just write them all out at this point. Okay, so this is going to be 7 plus 9 plus -2 plus 1 plus 8 plus -4 plus 4 plus 7 divided by 8. So this is simply the formula for the sample mean being applied to the differences directly. And then it follows that little s subscript d is the standard deviation formula. So the sample standard deviation formula being applied to the differences directly. The subscript d does not mean that we have to change the formula that we are working with. It is simply to help us differentiate between the standard deviation of the current, the standard deviation of the new, and the standard deviation of the differences directly. All right, so let's take a look at the hypothesis test in part B. Okay, so we would start off with the assumptions. So I don't believe that, okay, so our first assumption is SRS of observation. Well, we can just say SRS. So it's SRS of the differences, but this would be the same thing as SRS of the observations. So basically, were the cows randomly selected? And based off the information, we're not sure. The second one would be normality. And based off the description, we're not sure. And we only have 8 observations, so we would have to check this using, for example, a QQ plot or the Shapiro-Wilks test. Okay, on step 1, we have H0, mu D is less than or equal to 0 versus HA, mu D is greater than 0. And again, we have the greater than test here since the direction is new minus current. Had we have done the differences in the opposite direction, so current minus new, then we would perform a lower tail test to ask the exact same question. And I'll discuss this a little bit once I work through the rest of the steps. Okay, so then on step 2, we have our significance level, which I believe we said was 0.05. Yeah, 5% significance level, yep. Okay, and then on step 3, we can compute our test statistic. So we're gonna have T equals X bar D minus mu D over little sd divided by the square root of nd. So we have 3.75 minus 0 divided by 4.89 over the square root of 8. Okay, and then this is going to give us a test statistic of 2.169. All right, now on step 4, we can take either the critical value approach or the p-value approach. So this is going to work just like it has in all of the other illustrations that we have looked at so far. So we start by sketching out our t-curve. Okay. So for the critical value approach, we are going to have a critical value on t at 0.05 and 7, since the degrees of freedom are the number of differences minus 1 or the sample size minus 1. So it's simply 8 minus 1, which is 7. Okay. And now we go to our t-table. So we are matching t subscript 0.05 and 7, which gives us 1.895. So our critical value for this test is 1.895. All right. And then our test statistic was 2.169 or 2.169. So we can see that based off the critical value approach, we are inside the rejection region. So we could reject H0 based off this, this approach. Okay, so if we take the p-value approach, we mark down our test statistic. Okay, we have the green shaded area here. So this is the area of our p-value. Now in this case, we are conducting only an upper tail test. So the p-value is only the area to the right of the test statistic. So formally we can write p-value is equal to the probability that t exceeds 2.169. All right. So if we go to our t-table, we are on the 7 degree of freedom line. All right. So as we move across the line, we notice that 2.169 falls in between 1.895 and 2.365. So that means that our p-value will be located between 0.05 and 0.025. Okay. All right, so since, since 0.05 or 0.025 is less than the p-value, is less than probability t greater than 2.169 is less than 0.05, then 0.025 is less than the p-value is less than 0.05. Okay. So then on step 5, we can say reject H0. And on step 6, we can say at the 5% significance level, if the assumptions can be verified, then the data give sufficient evidence to suggest that that the population mean milk production increased on the new diet. Okay, so we can say at the 5% significance level, I forgot the word level, if the assumptions can be verified, because as you can recall, we couldn't actually verify either of the assumptions for this particular test. If the assumptions can be verified, then the data gives sufficient evidence to suggest that the population mean milk production increased on the new diet. Okay, so we have evidence that milk production actually went up on this new diet. Okay, in part C, we are asked to construct a 90% confidence interval. And then in part D, we're asked about the assumptions of each of the tests again. So for part C, we need to build a 90% CI. You'll notice that, well, actually it says, will a 90% confidence interval contain 0, and then to verify. So we are going to build it, but we're starting off with a question about the structure of the interval. Okay, so let's take a look at that. So in part B, we constructed a 1 sample t-test, and the critical value for this test was 1.895. This test gave evidence that the milk production increased on the new diet. In part C, we are going to build the interval. But first we are asked, should the interval contain 0? All right, well, let's start off by computing the t value for this interval. So we're going to have a t on alpha over 2, comma nd minus 1, which is a t on 0.05, comma 7, since we're building a 90% confidence interval. So you can see that this is the same critical value used in D, used in part B. So this means that we should have agreement between the confidence interval and the result of the hypothesis test. Now the confidence interval, or the hypothesis test rather, said that we should reject the null hypothesis, which means that we have evidence that milk production increased, which means that we have evidence that mu D is greater than 0. Okay, so since HT, the hypothesis test in B, gave evidence that mu D is greater than 0, the CI should have 2 bounds greater than 0. That is, it should not include 0. Okay, so the interval and the test will agree. We're using the same critical value. The hypothesis test gave us evidence that mu D is larger than 0. Therefore, the critical value should give us the same evidence. The confidence interval should give us the same evidence. For the confidence interval to give evidence that mu D is greater than 0, it must have 2 bounds that are both greater than 0 and not contain 0. Okay? So now we have to verify this. To verify this, we can simply work through step 2 of the confidence interval procedure. So we have x bar D plus or minus our t value multiplied by SD over the square root of ND. This is going to be 3.75 plus or minus 1.895 multiplied by 4.89 divided by the square root of 8. This is 3.75 plus or minus 3.277348. All right, and then this gives us a confidence interval with bounds 0.473 to 7.027. Okay, so then we can say that this has been verified. So we can see the confidence interval does not contain 0 and it has 2 positive bounds. So the confidence interval is giving us the same conclusion that the hypothesis test has given us. Okay, now I don't have much space, but let's go back just to look at this direction of the difference idea one more time. Okay. So some additional comments on direction of difference. Okay, so let's suppose that we took our differences as current minus new. Okay, so the result here would be that each difference now has the opposite sign. So we have -7, -9, +2, -1, -8, +4, -4, and -7. Okay, from this sample, we would then have x bar D is -3.75, and we would have little sd is 4.89. Now, if we wanted to conduct or answer the exact same question that was given in part B, the only difference here would be on step 1, we would have mu D greater than or equal to 0 versus mu d less than 0. So the direction of the difference, given that we want to ask the exact same question about mu d, influences the direction of the hypothesis test. So we are still asking, in this situation, is there evidence that the values on the new diet are larger than the values on the current diet? But because we took our differences as current minus new, if it is true that the new diet produces larger values than the current diet, we would now expect the mean of these differences to be less than 0. Okay. So if the values of current are truly smaller than the values from new, then the difference between them should all be negative or less than 0. So we are asking in this setup here the same thing that's being asked in B. So this is the same test shown before. In fact, if you work through the major parts of the test, on step 3, you'll see the test statistic now is simply negative 2.169. Okay, so the direction is flipped. And on step 4, the critical value, so the t on 0.05 comma 7, which is now a negative t, is just negative 1.895. So we are still in the rejection region, so we would still reject. So the direction of the difference influences the direction in the alternative hypothesis. So it's very important that we establish which direction the differences are being taken before we formulate our null and alternative hypothesis, so that we make sure we're testing on the right side of the curve. If it's a two-tailed test and you don't specify the direction, you can get away with it in that case because you have to test in each tail anyways. But for directional tests, it's very important that we understand which direction we're computing our differences in. All right. In part D, we're just asked what assumptions were made in B and C. We went over this at the start of part B. So we had the simple random sample assumption about the observations or about the differences, but that's the same thing. So basically we are just saying we assume each cow were randomly selected for the study, and that each cow is independent of the other. The second assumption was normality. So in this case, we have normality of the differences. So we only had 8 observations in this case, and we didn't have any information that that led us to believe that milk production in cows is normally distributed. So we would have to verify this assumption using something like a QQ plot or a test of normality like the Shapiro-Wilks test. Okay, so we have now seen 2 different examples of how to conduct 2 sample t-tests. To differentiate between the types of tests, we have to determine what kind of data we are working with. So if we have independent samples, then we would use the independent sample t-test. If we have paired samples or dependent samples, then we would use the paired t-test. For both tests, the relationship between the confidence interval and the hypothesis test is the same. So if the critical value for the confidence interval is the same critical value that's being used for the hypothesis test, we would expect the results from the interval and the hypothesis test to agree with each other. However, if the confidence interval is constructed using a different critical value from the hypothesis test, we won't necessarily have agreement between the solutions of each. In general, if we have this agreement between the critical value, if the CI contains 0, we would expect the null hypothesis of no difference to not be rejected. If the CI does not contain 0, then we would expect the null hypothesis of no difference to be rejected. Okay, so the relationship between rejecting H naught mu1 minus mu2 equals 0 or H naught mu1 or mu d equals 0 is rejected if the CI does not contain 0, and it is not rejected if the CI contains 0. All right, so that brings us to the end of this lecture set. As I mentioned before, this is all the material that we need for, well, actually I didn't mention this before. So this is all the material we need for lecture assignment 2. In the upcoming labs, you will probably see examples of two sample tests in SPSS. Again, we have our first quiz next Friday, but I'll send out an announcement about this as well via Blackboard. And on Monday, we'll start lecture set 4, which is on one-way ANOVA. So as always, if you have any questions, please let me know. And if not, I will talk to you on Monday afternoon at 1 p.m.